All right, so this last example, example 3, we are asked to calculate the flux of F. And they tell us that F is the result of taking the curl of some other known vector field A, which is actually given to us. So F is the curl of some vector field A. Call this A vector potential. So we want to know the flux of F outward through these two distinct surfaces whose common boundary C is the unit circle in the xz plane. Okay. Excuse me. So we can go ahead and quickly draw something reminiscent of what's going on here. So x, y, and z axes. Draw my circle here. Something like that. All right, delete this little bit. So there's our circle in the xz plane. And there's supposed to be two surfaces attached to it. So let's do two surfaces. One, maybe this is something like that. Okay. And let's make this a little bit more interesting. Let's put like a little hole here and like another little hole here. Okay. Let's try that one again. Okay. So if we're going to orient this, so imagine that we have this gear, okay, like this cog, right? This metal gear that's rotating this way. Why would we want it rotating this way? Well, if our orientation is outward, so there's our normal vector, it's outward, think about the axis of rotation in the right-hand rule. If we rotate this way, if we curl our fingers this way, our thumb is in that direction. So we want to have things curling or twisting in this orientation. So there you go. So if we're rotating in this orientation, imagine the swirl right here moving towards this boundary right here. So if this boundary had little teeth in it for a gear, right, something like that, and then we had this swirling, rotating gear coming towards it, right, so on and so forth, right? If it's rotating this way, then it's going to force this set of teeth to rotate this way. So one way we can think about orientation for a surface is first set your normal vector. Using the right-hand rule, what does that make your axis of what does that make your rotation direction? If this is your axis of rotation, the right-hand rule says this way. So now move that rotation to the boundary, and then you can see that as it rotates around, it will do that, which will force it to rotate this way. So our orientation here is like that. Okay. So that's S1. And now S2, let's just do something else here. Something like that. So one thing to keep in mind here is that this circle here, because it gets a little bit confusing right here, I'm gonna gray out this portion here. This portion, oops. Aw, what the heck? My whole little blobby thing went away. I don't know what happened. All right, here's another blobby thing. Call this S2. And then I'm just going to gray out this portion because this portion actually is like behind this red amorphous blob. Okay. So to add a little bit of depth here, let's just say it's sort of something like this. It's sort of curving, and maybe this has got something like that. Okay. Same thing here. The blue's got some sort of curvature here. Okay. So again, if we think about this, outward, so that's our axis of rotation, which via the right-hand rule means our rotation's like this. And now if you can imagine moving this rotation closer to this edge, then what's going to happen here, it's going to be like that. So it's going to be oriented this way, which will be opposite of the blue. Okay. So what this shows is that the boundary, excuse me, the boundary, so note, the boundary of S1 is going to be opposite the boundary of S2. So with that being said, let's go ahead and orient things, or let's parameterize things. So let's do this in blue. Oops. So for S1, the boundary of S1, let's parameterize it using some R of t. This is the circle in the xz plane, so I can parameterize this cosine t 0 sine t. Of course, for t in the interval 0 to 2 pi. Okay. Which, now that we have that, we can say that the flux of the vector field F through the surface S1 would be the double integral over S1 f dot ds, which is equal to, since f is the curl of A, we can replace f with the curl of A dot ds. Now that we have the double integral of the curl of something, we can use Stokes' theorem to say that this is equal to the line integral around the boundary of S1 A dot dr. Okay. And then we can go ahead and compute this as the integral from 0 to 2 pi this would be our vector field A, but we would replace x, y, and z with the x, y, and z from our parameterization up here. So this would be y plus z, so this would be sine of t, 0 plus sine of t. Sine of 0 is 0, and e to the 0 is 1, dotted with our derivative, which would be minus sine of t, 0 cosine of t dt, which is going to be the integral from 0 to 2 pi of cosine of t dt. Oh, I got my alignment incorrect, I'm sorry. This should be negative sine squared. I accidentally matched my zeros incorrectly. Sorry. So that's negative sine squared of t plus the cosine of t dt. And that is a fairly straightforward integral. This is equal to negative, let's see here. For this one, this should be negative pi. Okay? So now for the red, let's think about this. I'm going to move up here to the right here, do a little bit more room here. This is parameterized, let's say by R2 of t. An easy thing we can do here is just swap. Yeah, just swap this. and get sine of t, comma 0, comma cosine of t for t in the interval 0 to 2 pi. So we could do this directly, okay? We could do this directly. But I don't really want to do this directly because there's a better way we can do this. So this is how we would parameterize the boundary, del S2. And we could go through all of these same steps, but just over S2. And this would become the boundary of S2, and then we would import this new parameterization into here. So that's all good. But instead, let's think about this a little bit more. So instead, let's think about this. We know that the boundary of S1 is the opposite, or at least it's oriented oppositely of del S2. So this means that, for instance, if we want to know the flux of F through S2, we know that this is the double integral over S2 f dot ds. We can replace in the fact that F is the curl of A. And then we can use Stokes' theorem to write this as the line integral around the boundary of S2 A dot dr. Well, here's the thing. Since we know that del S1 is negative del S2, this is also the same thing as saying del S2 is equal to negative del S1, right? They're opposites. Doesn't matter what side that negative is on. So I can replace this del S2 with negative del S1, A dot dr. And if we reverse the orientation of a curve, all that does is put a minus sign in front of it. So we know what this is. This right here is just the, this right here is the flux of the vector field F through S1, which we found right here. This is equal to negative pi. So that means this is equal to negative pi, which is pi. So to revisit, or to just make sure we've answered everything, determine the flux of F outward through the distinct surfaces S1 and S2, whose common boundary C is the unit circle in the xz plane. Check and check. We've determined the two fluxes. The follow-up question is, if these two surfaces are glued together to form a closed surface, what is the flux through this resultant surface? Well, I guess I'll do this right in the middle here. If we define a new surface, let's say S1, so here, let's actually go through this way, sorry. The flux of F through this surface S1 union S2, glued together, in other words, this is the double integral over S1 union S2 f dot ds, which is just the double integral over S1 f dot ds plus the double integral over S2 f dot ds, which is equal to negative pi plus pi, which is 0. And this agrees with the fact that if we glue S1, since S1 and S2 share a common boundary, if we unify these together and glue them together, this would mean, so this is sort of another little way to think about it. Also, another way is that if del S1 is equal to negative del S2, then the boundary of the boundary of S1 union S2 is equal to the boundary of S1 plus the boundary of S2, which is equal to the null set, the set consisting of nothing. It's the set that is empty, it has nothing in it. It's the empty set. Okay, it's the empty set. So this means that the flux of F over this union surface is the double integral over S1 union S2 of F dot ds. And since F is the curl of A, we're running out of room. Whoops. Oh no. Let's just extend this. Continuing from up here, then this is we can use Stokes' theorem here to say that this is the line integral around the boundary of this, which is the empty set, A dot dr. Well, the line integral then must be 0, because this is integrating over nothing. So no matter how you look at it, we get the same answer.